Welcome. Have you ever wondered how a computer actually makes a decision? Or how a programmer can map out a massive application before they even type one line of code? Well, you've come to the right place. Today, we are pulling back the curtain on two concepts that are, and I mean this, the absolute bedrock of all programming.
So let's start with a really simple question. We all get how a recipe works for baking a cake, right? But how in the world do you write that same kind of recipe for a computer? Something so clear, so step-by-step, that it's literally impossible for it to misunderstand. That's the big idea we're going to unpack.
So here's our game plan. First, we're going to look at the simple true-false rules computers use to think. Then, we'll jump into something called pseudocode, which is kind of like the secret planning language for programmers. After that, we'll see how to write it, and then we'll put it all together and plan out our very first program.
All right, let's dive right in. Now, you might think computers are these super complex brains, but at their very core, they are incredibly simple. Every single decision they make, whether it's launching a rocket or just recommending a video for you to watch, boils down to one of only two possible answers: true or false. That's it. This whole system is called Boolean logic, and it's the language they think in.
Let's start with a rule anyone can get. You can play outside if it is Saturday or Sunday. See that tiny little word in the middle, or? That is our first key. If today is Saturday, can you play? Yep. If it's Sunday? Of course. But what if it's Monday? Nope. It's a super simple rule, right? Well, what's so cool is that computers follow this exact same logic.
So here's the deal with the OR operator. All you need is for one of the things you're checking to be true, and the whole statement becomes true. The only way you get a no or a false is if both conditions fail. So the only time you're stuck inside is when it's not Saturday and it's also not Sunday. You actually use this logic all the time, maybe without even realizing it, like when you search for cats or dogs online.
Now this thing here is called a truth table. It might look a little technical, but it's just a cheat sheet that shows every single possibility. Check it out. If X is true and Y is true, the result is true. If only one of them is true, the result is still true. See that last line? That's the only time you get a false, when both of them are false. It's the complete rulebook for OR.
And this is a perfect example of how a computer works smarter, not harder. It looks at that first part. Is 5 equal to 5? Yes, it is. That's true. Now, because this is an OR statement, the computer can actually just stop right there. It doesn't even bother checking the second part. Why would it? It's already found one true condition, and for OR, that's all it needs to say the whole thing is true.
Okay, now for our second operator, and this one is even easier. Seriously, just think of it as opposite day. It's like a logic switch. It takes whatever you give it and just flips it to its total opposite.
And yep, that's its entire job. Unlike OR, which compares two different things, NOT only works on one thing at a time. Its only purpose in life is to take a single truth value and just flip it. So simple, right?
And this tiny little truth table says it all. If your input X is true, then the output, not X, is false. And if the input is false, the output is true. It's a perfect mirror.
So let's follow the computer's brain on this one. First, it looks inside the parentheses. Is 7 equal to 5? No. So that's false. Then, it applies the not operator to that false result. And what's the opposite of false? It's true. And that's our final answer.
And hey, here's a quick little fun fact for you. This whole system of true-false logic that powers pretty much everything in our digital lives, it's named after a guy from the 1800s, a mathematician named George Boole, who came up with all these rules in the first place. Pretty cool. All right, so we've seen the tiny little Lego bricks of logic. Now let's move on and look at the blueprint. How do we take that simple true/false thinking and use it to plan out an entire program? So what in the world is pseudocode? The best way to think about it is as a planning tool. It's the bridge that connects a human idea to the super strict language of a computer. You write it in plain English for yourself and other people to map out the logic before you get tangled up in all the specific rules of a real language like Python or Java. This right here is the absolute best analogy. A recipe tells you to preheat the oven and mix the flour and sugar. It doesn't get into the nitty-gritty chemistry of how baking powder works. In the exact same way, pseudocode lays out the big steps, like get the user's name or calculate the total, without getting bogged down in the specific character-by-character code that makes it happen. And you know, that's a fair question. If a computer can't even run this stuff, why bother? Why waste time writing a plan when you could just jump right in and start writing the actual code?
Because, and this is so important, planning is always faster than fixing. Think about it. An architect draws a blueprint before anyone starts building. Pseudocode forces you to think through the whole problem from start to finish. And trust me, it is way, way easier to spot a mistake in your simple English recipe than it is when you're staring at 200 lines of complicated code. Okay, so we know what it is and why it's so useful. Now for the fun part. How do we actually write it? And the good news is, it's designed to be incredibly straightforward.
You really only need to know these few keywords to get started. You just wrap your whole plan in begin and end. When you need to get some info from a person, you accept it. When you need to show them a result on the screen, you display it. And those two little slashes, that's just for writing notes to yourself that are completely ignored. It's really that simple.
All right, enough theory. Let's see this stuff in action. We're going to walk through a couple of classic examples and write the pseudocode plan for them, putting everything we've just talked about together. So, let's start with something simple. A plan to add two numbers. Look at the structure. We start with begin. Then we accept two numbers from the user. We'll just call them x and y for now. Think of them as empty boxes waiting for a value. Next comes the core logic. Create a new box called sum and put the result of x plus y inside it. And finally, display whatever is in that sum box and finish up with end. It's a complete logical recipe.
Okay, now look at this next one for finding the area of a square. Do you see the pattern? It's the exact same structure. Begin, then accept the length of a side. We'll call it s. The actual calculation is different, of course. This time area is s times s, but the flow is identical. Display the area, and then end. This simple framework can solve a ton of different problems.
And really, that's what this all comes down to. The big secret of programming isn't about memorizing 100 commands in a specific language. It's about learning how to think in a structured, step-by-step way. Pseudocode is the tool you use to build algorithms. An algorithm? That's just a fancy word for what we've been doing this whole time, creating a recipe to solve a problem. Mastering that skill is the real heart of being a programmer.
So, what's next? You now have the basic tools to start thinking like a programmer. So I'll leave you with a challenge. Think about a simple task you do every day: making coffee, picking an outfit, deciding what to watch on TV. How would you write the pseudocode, the clear step-by-step recipe for that decision? Give it a shot. That's your first real step into this amazing world of programming logic.